Hi, now we are going to talk about nuclear physics, basics, and a slightly higher point. Representation of an atom. Generally, atom is represented. Say X is an atom. X is at a Z, we call it as atomic number. A, we call it as mass number. Atomic number means number of protons. Of course, we know every atom has got same number of protons and same number of electrons. Atom is electrically neutral. But Z means atomic number, number of protons. Mass number, number of protons plus number of neutrons. Okay, so this is the representation of an atom. What is called size of the nucleus? Nuclear size. All is equal to R naught A power 1 by 3. R naught is a constant. 1.3 Fermi, femto Fermi, 10 power minus 15 meter. You know very well A is called the mass number. So any particular element, if you know the mass number, substitute the value, calculate the radius, nuclear radius. So it is in the order of 10 power minus 15 meter. Nuclear size is in the order of 10 power minus 15 meter. Size of an atom, 10 power minus 10 meter. Angstrom unit. Angstrom unit, 10 power minus 10 meter. Size of the nucleus is in the order of 10 power minus 15 meter. Size of the nucleus is in the order of 10 power minus 10 meter. Sir, depending upon the atomic number and mass number, we can categorize the element into 3 types. Isotopes, isobars, isotones. Elements having same atomic number but different mass number. Same atomic number, different mass number. We call it as isotopes. 1H1, 1H2, 1H3. Atomic number is 1. Mass number is different. Hydrogen, deuterium, tritium. 6C12, 6C14. Carbon. Atomic number 6, mass number differs. 92U235, 92U238. Uranium. Atomic number same, mass number different. Isobars. 2 different elements having same mass number but different atomic number. 2 elements. So why 2 elements? When you say atomic number is different, element should be different only. 6C14, 7 and 14. See, mass number is same, but this is carbon, this is nitrogen. 3Li7, 4Be7, 7, but this is different. 2 different elements. Same mass number, different atomic number, 2 different elements. Then we call it as isobars. Isotones. Isotones means 2 different elements having same number of neutrons. Neutron number is same. How's that? 6C14, 8O16. How to calculate neutron number? Atomic number is Z, mass number is A. Atomic number means number of protons. Mass number means number of protons and the number of neutrons. So when you want to calculate neutron number, A minus Z will be neutron number. A is 14 here, Z is 6, 14 minus 6, 8 neutrons. Here 16 minus 8 neutrons. Two different elements having same number of neutrons, we call it as isotopes. Next term. What is called mass defect and what is called binding energy? Mass defects. There you calculate or you consider silicon 14Si28. Sodium 11Na23. Any example you take, no problem. So 11 protons plus 12 neutrons you have. The sodium nucleus, if you take, mass of the sodium nucleus, you take it as M1. Mass of 11 protons and 12 neutrons, you take it as M2. This mass is M1. Nuclear mass, sodium nuclear mass is M1. And the mass of 11 proton and 12 neutron is M2. Actually speaking, these two should be same because inside the nucleus you have 11 protons and 12 neutrons only. Theoretically, it should be same, but practically, if you see proton mass and neutron mass, when you say M2, that is slightly more than the nuclear mass. These two masses are not equal. That difference in mass only we call it as mass defect. Represented by delta M. How the rates are M2? M2 is mass of the proton. How many protons we have? Z protons, ZMP. Plus mass of the neutron. How many neutrons we have? A minus Z number of neutrons into Mn minus capital M nuclear mass. You calculate, that is called delta M, which is positive. Generally, mass of protons, mass of neutrons will be in the order of proton mass, neutron mass will be in the order of 1.66 into 10 power minus 27 kilogram. Electron mass we know 9.1 10 power minus 31 kilogram. We are studying here only nuclear mass. Nuclear means proton mass, neutron mass. So proton mass, neutron mass nearly, actually neutron mass is slightly more than that of proton. Slightly more. The nearest value of proton and neutron mass is 1.66 into 10 power minus 27 kilogram. So, is that how many protons you have into proton mass? How many neutrons you have neutron mass? You calculate substitute. Any particular element you can calculate mass defect. The kilogram in 10 power minus 27 kilogram you are having. Your mass is also we are representing in kilogram. Proton, neutron, electron also kilogram. 10 power minus 27. 10 power minus 31 kilogram. So for convenience sake, we are representing the mass of protons and neutrons in terms of atomic mass unit. One atomic mass unit means mass of 1/12 of C12 atom carbon. 6C12 carbon. So 12 nucleons. Common name for proton and neutron, we call it as nucleons. So 12 nucleons mass. Divide by 12 you are calculating. That means 1 nucleon mass. So 1 nucleon mass is 1 AMU. Nearly 1.66 into 10 power minus 27 kilogram. So if you want to represent proton mass, neutron mass directly in terms of AMU, you can write. Anytime you can convert 1 AMU equivalent in kilogram is 1.66 10 power minus 27. So proton mass is nearly 1.007266 AMU. Mass of neutron 1.0086. Slightly more. Proton mass, neutron mass. 1 AMU only, slightly different. 1.007, 1.008. That's all. Okay, sir. Why is this difference, sir, in mass is coming? When these protons and neutrons are combined, there is some loss in mass. There is some loss in energy because there is some loss in mass. How to calculate the energy loss? For that, you should convert this mass in terms of energy first. 1 atomic mass unit mass, you know, man. Convert the energy equivalent of this 1 AMU. Then we can go for that. Okay. So energy equivalent of 1 AMU. Energy equivalent of 1 AMU. One, of course, you know very well, E is equal to mc square, Einstein's mass energy relation. So 1 AMU energy equivalent means delta M into C square. One delta M value mass is how much? 1.66 10 power minus 27. C value 3 into 10 power 8 the whole square. This is energy equivalent of 1 AMU given in joules. You want to convert this in electron volts. So 1.66 10 power minus 27. 3 square 9. 10 power 8 square is 10 power 16. Divided by 1.6 10 power minus 19. Already we have discussed in joules to electron volt. If you want to convert, divide by the charge. Calculate 1 AMU energy equivalent. Minus 27 plus 16 is minus 11. Minus 19 will go as plus 19. Rearranged, you will get 931 million electron volt. MEV, 10 power 6 electron volt. 9.31 10 power 8 you will get, that is 931 into 10 power 6 electron. So 1 AMU energy equivalent means 931 MeV. Sir, what we are going to do with this? Suppose when protons and neutrons are combined, energy is released. That is the information you have given. Energy is released means to calculate that energy equivalent, every time you need to multiply by C square and divide by 1.66, 10 power minus 19. Directly you multiply by 931 MeV. Mass is given, Calculate energy equivalent means multiply by 931 MeV. Provided that mass should be in terms of AMU. Kilogram means you cannot convert. Kilogram means converted in terms of AMU, then multiply by 930. Here write an example. Okay. Delta M is ZMP plus A minus ZMN minus nuclear mass. Delta E, delta M into 931 MeV. This is called binding energy. Energy required to bind all protons and neutrons together. Sir, how can I calculate binding energy for a particular element? Only one thing you should know. What is the nuclear mass? If they give nuclear mass, delta M you can calculate, delta E you can calculate. You take sodium. That example only we have taken sodium. 11 Na23. 11 proton mass, 23 minus 11, 12 neutron mass minus mass of nuclear mass of sodium. Say you are getting around 0.055 AMU. This is in AMU, this is in AMU, this is in AMU. Everything in AMU, then we can calculate. 0.055 AMU, you are getting delta M. Binding energy, I want to calculate. What is binding energy? Delta M 0.055 into 931 MeV multiplied. This is the energy required. You will get some value in MeV, no? That is the energy required to split the protons and neutrons. Energy required to dissociate the protons and neutrons in sodium. Okay, sir. When 11 protons and 12 neutrons are combined, some energy is released. This is the energy released. Either way you can tell. You have a sodium nucleus, you provide this much energy, delta E. 11 protons and 12 neutrons will be separated. Energy required to dissociate protons and neutrons. Now associate. When you combine 11 protons and 12 neutrons are together, then binding energy is released. So like this, for any element you can calculate mass defect and binding energy. Only nuclear mass of that particular element should be given. Clear, ma? Fine. Nuclear density. You know very well, density is mass by volume. Mass means nuclear mass. Nuclear means how many nucleons present. Total nuclear mass we want. So total nucleons is nothing but mass number. Mass of one nucleon, not neutron, proton or 1.66 10 power minus 27. Substitute. How many? Depending upon the element. Divided by volume, spherical in shape, 4 by 3 pi r cube. A into Mn by 4 by 3 pi. Already we have studied the size of the nucleus. R is equal to R naught A power 1 by 3. So R naught A power 1 by 3, the whole cube. So I will get A into Mn divided by 4 by 3 pi R naught cube A power 1 by 3 the whole cube, that is A. Cancel. Nucleon mass is substitute. R naught is a constant 1.3 Fermi whole cube, substitute. You will get density of nucleus around 2 into 10 power 18 kilogram per meter. 10 power 17 to 10 power 18 kilogram per meter cube you have, that is nuclear density, which is the maximum. Extraordinary high value density, what is the meaning? Nucleus is that much stronger. It is not easy to break the nucleus. More denser. Some energy should be given to break the nucleus. So, this is nuclear density. So, we have discussed about mass defector. We have discussed about binding energy. You draw a graph. Binding energy per nucleon. Any particular element, you calculate binding. From hydrogen atom to uranium, you calculate binding energy. Divide by that particular element mass number. B by A, take it in y-axis. A, you take it in x-axis. This is expressed in MeV. 20, 40, 60, up to 200, 220, 240. A value. So every element from hydrogen to uranium, you calculate binding energy, divide by its mass number to calculate binding energy per nucleon. Should be in MeV only. This is the nature of the graph. See, beyond 200, binding energy per nucleon decreases. Here and all, you are getting some peaks. Lighter element possesses more binding energy per nucleon. What for this graph, sir? Three things we can use this graph. Number one, the particular element is stable or not. Graph will tell. More binding energy per nucleon means more stable. Nuclear fission, process of breaking. Depending upon binding energy per nucleon, you can calculate whether it is applicable for fission or fusion, process of combining. So, to indicate the stability, elements required for fission or elements required for fusion. Binding energy graph. Stability, indicate the stability is most important. So, maximum binding energy per nucleon is 8.8 MeV, that is for iron, 28 Fe56. Binding energy per nucleon is maximum for iron. Average binding energy is 8.5 MeV, but here 8.8 MeV.